Okay, great. My face will be in the corner, so if I block anything, I'll be able to just move that over. So what we're doing today is image classification using a neural network called convolutional neural networks, or CNNs for short. I'll explain why that's the main neural network to use, why I'm using image classification at all, and what the purpose of this particular project is. So as I mentioned earlier, I do have a decent amount to go over. I'm going to introduce the purpose of the project, what problem I aim to address with this project, and the significance, the practical usage of any answer that I would achieve through this project. I'll explain what the CIFAR 110 is, as well as the data inside it. And I'm going to set up the data by manually loading it, splitting it in a typical supervised fashion between testing data set, training data set, and I'll also have a small holdout portion for validation as well. Being that this is an image classification data set, I would be remiss if I didn't go ahead and at least show you a couple of images during that time. Another thing that I wanted to do is to experiment with dimensionality reduction techniques. I'll explain why I'm doing that at all, and I'm also going to explain why those end up not really working all that well when applied to image type data sets. Before I jump into the actual meat of the project, the supervised modeling, I want to do a little bit of unsupervised modeling analysis, spectral clustering, TSNE, and LDA, comparing that to the previous ones. For supervised modeling, again, I'm going to be focusing strictly on CNNs, and I'll explain why that is. And what I have for you is 4 different CNN architectures all through the Keras library. And what I want to see is how the images work in relation to all these various CNNs. And then once I get those results, I'll analyze them, show them in graphical format, and come to conclusions for the purpose of this data set. So why work with image classification? As you can imagine, it is a significant portion of data science work that can be done. There's a wide range of applications for this kinds of data set. I'll give you some examples. There's GPS, facial recognition, anything that really has a spatial character to it, a spatial relationship that's needed. CNNs are going to be the model to use. And something as simple as taking photos of an accident scene, that alone lends CNN work to all insurance companies. So again, there's a wide array of applications that can be used for this kind of data. And one that I didn't mention here is, of course, object recognition. It's a big thing in the data science world, and what's important about it is that they become more and more sophisticated as the years go on. Not only does more sophisticated object recognition models pick up different kinds of objects, more and more classes to be added to the algorithm, but classes that are already in the system become more and more specified. So the example that I give is going from a soda can to having an object recognition model identify it as a Pepsi can or a Diet Cola can. And the importance of this is that these models are going to be becoming more and more complex, and anytime a model becomes more and more complex, the time to train those kinds of models is going to essentially exponentially increase, and in doing so, it's going to demand much higher computational resources as well. So what I wanted to focus on wasn't actually the user side. which is having your phone, taking a picture, and having the algorithm on your phone say, that is a Pepsi can. I actually found that there's a big demand for figuring out how models can be trained in the image classification arena. Again, every time that you get a new class, you have to train these models, and having a neural network, which is already a very complex machine learning model, is going to demand resources beyond what I have on my computer. And we'll see later on that even the models that I've used took a significantly long time to train these models. So I wanted to focus on the training itself and less so about predictions and less so about accuracy. And so the problem that I am presenting today is which object recognition model is going to achieve the highest efficiency. I define efficiency as a ratio of testing accuracy to the amount of time it takes to train that model. And as I mentioned before, this is really more intended more for the company side that has that demand for training, and it has that wide range of resources that needs to be tapered down for just cost purposes. I'm going to be, moving my face from time to time. So the data set that I use today is the CIFAR data set. It's an acronym for Canadian Institute for Advanced Research. And the CIFAR is actually a collection of two different data sets, the CIFAR 10 and CIFAR 100. As the name implies, one has 10 classes, which are actually shown here, a couple of machines and the rest being animals. And the CIFAR 100 is essentially the same, but 100 various classes, branching out to buildings, trees, pieces of furniture, but all objects. And the beauty of the CIFAR is that one, it's already set up for you in terms of having balanced classes and a uniform amount of data points. So both CIFAR 10 and CIFAR 100 are going to have 60,000 images, already split 50,000 train, 10,000 test points. Each class is going to be perfectly balanced with 6,000 images. And a really important point is that every data point is going to have the same shape and the same size. Every image that we're going to be working with today is going to have the resolution of a 32 by 32 pixel image times 3 for each color channel. And that's going to yield, if you do the math, 3,072 different kinds of features. Each feature going to have values between 0 and 255. You're going to see I'm going to normalize that down just for consistency purposes. And because this is a popular data set, I would say almost as popular as the MNIST. That's the one with the handwritten numerals that you'll find immediately when you type into Google image classification data science. I wanted to change it up a little bit and create my own data set called the CIFAR 110. And all that really is just adding the extra 10 classes from the CIFAR 10 into the 100 data set, making it a little more complex, switching it up from, again, the CIFAR sets that have been used many times before by other data scientists. And just as an example for just how popular the CIFAR is, you can actually directly load it from the Keras library. I didn't do that because CIFAR 110 is something I made up. So that's actually a typo. It should say CIFAR 10, CIFAR 100. And I also want to compare the analysis of CIFAR 110 to CIFAR 10 to see if models are more conducive and appropriate to a smaller image classification data set as opposed to a larger one. And so because I'm creating this new data set, I did have to do the manual loading from the CIFAR website. And what you get after you what's called unpickling when you're doing the loading via the Python pickle library is that you get a variety of dictionaries, one being the actual arrays of the pixel features, another being the class numbers, another being the class label names. Um, so I won't bore you with the actual loading part. But one thing that I will mention is that when you directly load it from the CIFAR website, it's in a 1D array format. And so what you'll find for Keras is that it's very particular, very finicky when it comes to what kinds of shapes are being inputted into the neural network model. So this is just an example function that I created to convert that 1D array into the 32 by 32 by 3 that we want. Again, the data is already split, and I performed some work applying those extra 10 classes into the CIFAR 100 just to make sure that they're shuffled to minimize bias, as well as keeping those classes the same exact size to maintain class balance. So as I mentioned during the table of contents, you can't have image classification without looking at a few images. 32 by 32 by 3 is not all that many pixels. So even for that size, a fraction of my screen, it's already kind of blurred out, which is really just a testament that for how long these neural network models take, even for something as low resolution as this, emphasizes that much more how important training is to maintain time as well as computational resources. And that's really what I just said there, at least for my lowly laptop. Having it kept at 32 by 32 by 3 is fine by me. One major pre-processing thing that I did was just normalize the values. Again, the 0 to 255 is a scale of how bright something is. And when you have 3 color channels, each channel is going to have 0 to 255 for a given pixel, and a combination of the RGB produces whatever color is on the image. And this is just another example of when you expand and scale up these 32 by 32 by 3, really low resolution. So this is just another example that neural networks really need to have simple data so it doesn't get overloaded computationally. There are a number of data manipulation things that you can use. There's a lot of SciPy library things that you can use to adjust the image. I will represent to you now that I didn't do any of this for purposes of my actual project, but I wanted to give you an example of what is out there. You can focus more on the edges of an image for contouring. You can blur it, you can rotate it, you can sharpen it. I think I sharpened it just a little too much in that particular image. And you can also, quote unquote, fill in the blank spaces if something is a little too blurry via interpolation. And there's a couple of different kinds of interpolation done here. You can definitely go down a rabbit hole with image pre-processing. That wasn't the focus of this particular project, but I wanted to just bring it to your attention that that avenue is there. So I had mentioned a number of times thus far that convolutional neural networks are very complex, and complex models demand a lot computationally as well as just temporally. It just takes a lot of time to train these kinds of models. So even though in the grand scheme of things, 32 by 32 by 3 isn't that large of a resolution, 3072 images, I'm sorry, 3072 features isn't that much in the grand scheme of things. If I can definitely reduce that number down to say 50, it's going to make it that much faster. So why wouldn't I? I do hypothesize that when we're trying a dimensionality reduction technique, such as principal component analysis, and that's just one of a few algorithms out there, flattening something down to a completely different image is going to lose that spatial relationship that's so necessary for image classification. So I don't imagine PCA helping in this regard, but I wanted to raise it to establish that you got to try. Intuitively, again, it makes sense that it's probably not going to work. You don't want to take something with a spatial relationship and destroy that spatial relationship. But there is an importance to the word scientist in data science. Again, you have to try. So what I did was I took a basic feed-forward neural network called a multi-layer perceptron and ran the images through just for baseline before dimensionality reduction is done. I got a 43% accuracy on the testing set for CIFAR 10, which is actually pretty good considering that multi-layer perceptrons are not really used for image classification. Unfortunately, it didn't work all that well for CIFAR 110. That is essentially the null accuracy. And when I say null accuracy, I mean if the model is simply guessing the most prevalent class, what accuracy would you get? And the guessing value here, 1 over 11, is about 0.9%. So that's not all that good. And when I applied PCA, I wanted to figure out how many components should I reduce this data down to. As you know, when you're reducing real data down into something that's compressed and flattened, you're going to lose some of the explanatory power that you see in the data set. For variance, you're going to lose some of that variance in that data. PCA is pretty good for maintaining variance, especially in relation to a lot of other dimensionality reduction techniques. But nonetheless, you still lose stuff when you reduce those dimensions down. So what I did was I created a function that tried to maintain that much variance, 0.857, but still have the lowest amount of components possible, the lowest amount of features. And after running this function, I found that for the CIFAR 10, I can achieve this minimum variance with only 59 features and only 51 features for the CIFAR 110. But as you'll see, it doesn't help. The hypothesis was correct. It does destroy that spatial relationship, dropping the accuracy on the testing set for CIFAR 10 from 43 down to 20. Can't really go that much less than guessing accuracy, null accuracy. So 1% on CIFAR 110 was maintained. Obviously, we're inputting data with only 51, 59 features as opposed to 3072, it's going to complete much faster. And that's what we see here with the hundreds of seconds down to only dozens of seconds. And just to emphasize the point that dimensionality reduction is not appropriate for image classification, I can represent to you that I quintuple checked that the original image of this fighter jet is indeed the same image on the right side for PCA. You can see that the components have been reduced down to beyond recognition. Just again emphasizing that this kind of work is not really appropriate for image classification. So before actually jumping into the supervised modeling, I wanted to gain some information about the data set. I wanted to see how clusters would be made in between the various classes. Out of all the clustering algorithms that are out there, spectral clustering is probably the best to use for image data. I'm of the opinion that it's still not really all that appropriate for the reasons that you're, again, trying to flatten down a spatial relationship onto essentially a graphical set of clusters. But the pairwise calculation is a little more conducive to pixel by pixel analysis. TSNE follows a gradient descent model. That's essentially the model working over and over to minimize the loss function or the cost function when doing that clustering. It's very computationally heavy. We'll see that both spectral clustering as well as TSNE doesn't really work all that well. And as a final unsupervised model, I'm going to use linear discriminant analysis. It's pretty similar to, there we go. It's pretty similar to SVM in that it creates a hyperplane and tries to separate the data points as best as possible and trying to maintain those classes. It's not technically unsupervised model simply because you need to have those class values inputted. I still grouped it under these unsupervised models simply because the extent of the effect of class input is really just for labeling purposes. But I just wanted to raise that. I would say the main difference between LDA and SVM is that although they both end up with the same calculation, trying to maximize the distance between classes, LDA performs a pairwise analysis, much like spectral clustering. SVM doesn't do that. One thing I will mention is that pairwise analyses are always computationally heavy, so that was just one thing that I had to work with. So as I mentioned, spectral clustering really isn't all that helpful. This is essentially random. You can see that I used 4 clustering points. I cannot tell you where those centroids are based on this graph. So this didn't really all help that much. For all these unsupervised models, you'll notice that I'm only using CIFAR 10 just because it's impossible to graph 110 different classes. The beauty about TSNE is that it allows a spreading out of data points as best as possible. And obviously in doing so, you're going to see the separation of classes as best as you can. But what we see here is actually quite the opposite. We see that the data points on TSNE are tightly clustered, and PCA is spread out to the point that you can make out some general trends within the CIFAR 10 data set. And the reason why this is the case is simply because I didn't give it enough iterations for TSNE to run its course. You'll see in the text on the left that I use the hyperparameter max iter to limit it to only 300 iterations. And even only 300 times, it still took 645 seconds, well over 5 minutes to produce that. So the computationally heavy component to TSNE is a little understated in my opinion. And in contrast, emphasizes just how good of a baseline separation of data classes you can get from PCA alone, even though we've established previously that PCA isn't really all that good for image classification. So for the final thing, LDA, like spectral clustering, uses a pairwise analysis. I already mentioned that takes a very, very long time to do. And if you ever used SVM, you'll know that SVM is also notorious for taking a very long time to do, demands a lot from your terminal. So instead of using all the data points, 60,000 data points, 50,000 in the training set, I only worked with 2,000 data points. You can even see working with just such a small fraction, it still took 95 seconds, over 2 minutes for CIFAR 110. Really not getting all that strong of an accuracy score in terms of a classification analysis. But we'll see that out of all the unsupervised models, LDA, even for 2,000 data points, did produce the clearest clusters available. And when I say clear clusters, you can make out the orange data points in the bottom left. Red and purple are clustered. Off green and lime green are clustered. And what we see here are the expected kinds of clusters. Let me rephrase that. The expected kinds of things that would be clustered with each other. So bird, cat, and deer are clustered. The machines are clustered together. And kind of a unfortunate thing, it tells us something that we already know. But I would argue that that's something that within itself is information, that we know that there's no erroneous data trends or some odd data that doesn't really fit the intuitive pattern that we're going to look for. So this LDA plot definitely helped us when we were doing our unsupervised modeling. And so I had already mentioned that LDA is by definition a supervised modeling process. I do have to include those target labels. So I found it a little apropos to use it as a transition to the supervised learning portion of this project. What I used for the supervised learning models were convolutional neural networks, CNNs. And I'll tell you right now, those are the only kinds of supervised learning models that I used. As I mentioned again, the reason why is because out of all the various supervised models out there, convolutional neural networks are the model to use to accommodate and account for that spatial relationship. And the main way that it does that is, as the name implies, the convolutional component to it. And when I say that, I mean that the model begins with taking a hyperplane called a kernel, and it hovers over an area of the image and convolves it down to kind of a more compressed set of features. And what those numbers mean, the 4, the 3, the 4, is essentially a value based on that general area. So you're accounting for the spatial relationship of each pixel along with the pixels around it. Very computationally heavy, but this has been found to be the most accurate in accounting for that spatial relationship. As you see on the bottom, other machine learning models just simply don't do that. So I can go into great depth in terms of how CNNs work, a little beyond the scope, and quite frankly, along with all the other artificial neural networks, they're very complex, black box for the majority of it. But to give you a brief overview of what is happening layer by layer within the network is that you take the input data, obviously an image in this case, and it performs that convolutional operation that was just discussed in the previous slide. Doing that is very computationally heavy, and applying that to another layer is going to only exponentially multiply the number of convolutions to the point that the data is just going to slow your model down to a halt. And so in order to keep the number of parameters low after doing these convolutional operations, we add what's called a pooling layer, where it takes the same exact process. It takes a hyperplane kernel, hovers over the convolved feature, and pulls it down to a much more reduced number of features. You then use that for the next set of layers, whether it be an additional convolutional layer or you just jump right into the output layer, also known as the fully connected layer. And that is where you get your predictions. So the steps of convolution: take your input data, you run it through convolutional layers, you pull them down in a process called downsampling, and then you flatten all that data into a one-dimensional list of probabilities, and that's your output. One thing that's not mentioned here is that that's only one iteration of a convolutional neural network. It kind of boosts itself in the sense that it takes all the weights that it generated. And when I say weights, I mean from layer to layer, it calculates the best way to minimize the loss function in terms of the relationship between what it predicts and the actual Y true output. And it keeps those weights from the previous iteration, runs it through this exact process a second time, through a second iteration with those weights, gets another set of output predictions, updates the weights, and it continues on until however many iterations you say is done. In the neural network arena, we don't say iterations, we say epochs. And just as a standard that I use for both CIFAR 10 and CIFAR 110, I kept it limited to 20 epochs. So for this convolutional neural network analysis, I experimented with 4 different CNN architectures. A simple CNN, just one convolutional layer, then it goes into that fully connected output layer. The second one, I incorporate 3 convolutional layers. You'll see that doing that really exponentially expands the amount of connections, the amount of parameters that you're going to be getting, and in turn increases the amount of time it takes to train. So going from 2 to 3, I experiment with the same kind of thing, same amount of layers, but I keep the layers small, from 64 nodes in the 1 and 2 down to 32 nodes. And to wrap everything up, as the 4th CNN, I incorporate a little bit from the previous 3 to see if the whole is better than the sum of the individual parts. So for the CNN architecture, whenever you run a Keras model, and if I hadn't made this clear earlier, all the CNNs that I'm working with is through the Keras library. It's really good for a fast construction of a CNN. It works natively very well with Python, which is another reason to use it. You can do less with it than some more sophisticated things like TensorFlow, but for purposes of this project, I stuck with Keras. So here's an example of the architecture of a CNN. You'll see, and I'll use my cursor, it's in a sequential format. You go from left to right. There's no like looping back or anything. The only looping back is when the whole sequential format is complete and you loop back as a second iteration. But it's from a left to right, or I guess in this case, a top-down format. You start with a convolutional layer, having your input shape be 32 by 32 by 3. I just set input shape as a specific variable for that. You pull it down. You'll see that the kernel size is a 3 by 3, so that is the size of the hyperplane that hovers over the 32 by 32 image, with a 2 by 2 hyperplane for pooling layer. The dense layers at the bottom are that fully connected layer that I was mentioning, having that one-dimensional array of probabilities for each data point. And the only thing that I haven't mentioned is the dropout. All that is just telling the model that when you're going from the pooling layer to this next layer, I want you to focus on only 75% of the weights, 75% of the nodes. And the purpose of that is to minimize overfitting. CNNs, neural networks in general, actually are notorious for overfitting just because they're that good at achieving accuracy. So it's really necessary to have those dropout layers included. I don't really have time to explain what the loss function is or how the optimizer works. If there is time at the end, I'll be happy to go into a little more detail about that. This kind of summary output on the right-hand side of your screen is kind of an example of the various shapes that is seen from layer to layer, how many connections, also known as parameters, that you're going to see made from layer to layer. Almost 1 million connections. You can see that it's going to be pretty complex. So after running this model through CIFAR 10 and CIFAR 110, as simple as it is, it's highly overfit. You'll see that when I'm comparing the red line, that's the training set, to the golden line, the validation set, And again, just to reiterate, the validation set is just a 10% holdout from my training set. The testing set is completely separate from those two things. You'll see that both for CIFAR 10 and CIFAR 110, when you get to EPIC 20, it's significantly overfit. So that's something that I aim to fix for CNNs 2 through 4. But even as simple as the simplest CNN that I had taken a look at, you can see just how long it takes to train these models. 806 seconds for CIFAR 10, 856. You do the math, that's well over 10 minutes. Just having my computer sit around expending 100% of my CPU, several gigabytes of RAM needed to be used for these calculations. I had my fingers crossed during the whole time that I was running these models that my CPU wouldn't melt into liquid. Didn't happen by virtue of me doing this project, but you can see just how computationally heavy these things are. A couple of quick notes before I go on to the next slide. A first note is that, as I mentioned before, all of these calculations are limited to 20 epochs, 20 iterations. I incorporated what's called an early stopping mechanism, and the only time that kind of came into effect was with CIFAR 10. You'll notice that the lines stop at about 16 epochs instead of 20, but the rest of them are 20 epochs. And the second note I wanted to make is that the graphs are not directly compared to scale. You'll see that for the CIFAR 10, the ticks go up to above 80% accuracy, with the CIFAR 110 only achieving less than 50%.
Excuse me, John.
Yeah.
May I hop in here for a sec? Yeah, so I'm loving everything I'm seeing, and I just want to make sure that we keep enough time for some Q&A.
Sure.
And not everyone can stay right till the end, or technically we want to wrap up like just in 5 minutes, but usually we go till the end of the hour. But I just wanted to jump in because you've covered a lot of great information, and it might be a good idea for us to also engage in some dialogue. So I just wanted to share that with
you.
Okay.
Yeah, I'll wrap everything up in the next 60 seconds.
Cool.
Multi-layer, I did 3 convolutional layers, as I had mentioned before. It's more complex than the simple CNN, so the complex times are significantly longer. Now it's nearing 20 minutes, over 20 minutes for CIFAR 110. At least this model is significantly less overfit. Because the previous one took a very long time to do, I thought that having smaller layers would mean smaller connections meaning a faster training time. And surprise, surprise, it took 40 and 50 minutes to have these trainings be complete. And after combining everything, pooling layers, multiple convolutional small layers, that actually turned out to be the longest. So when comparing all of the neural networks side by side, we see that the multi-layer CNN is the second most efficient. Looking at this particular graph, the accuracies are higher per 20 epochs per minute of training. But the simple CNN is actually also the most overfit. So if we're asking ourselves which supervised model provides the best accuracy, efficiency trade-off, that's again testing accuracy per minute, I'm going to go with the multi-layer CNN, because even though the simple CNN was technically better than the multi-layer, it was also the most overfit. 3 quick questions that I wanted to mention is that why didn't I use other metrics? Why did I only focus on accuracy? They don't really translate all that well for a multi-classification data set. There's really no such thing as a false positive when you're looking at multi-classes. Second question is, why is training focused on here? when you want to focus on predictions. Just to reiterate, I wanted to focus more on the company side that does have an interest in minimizing costs, minimizing training time and computational resources. And for the third and final question, why again did I use a CIFAR 110? Well, I just wanted to, I guess, be a little different. CIFAR data sets have been used ad nauseum, so I wanted to explore how CNNs would work under a completely different data set. So I did go a little over time, and I apologize, but I hope that there is still a bit of time left for questions. So thank you.